So up next is Mike MacCoss from the University of Washington Department of Genome Sciences, and Mike's group has been doing DIA for a very long time. I think probably longer than our group also. And while we do things, I think similarly in some ways, there's also some things that we do differently, and it's interesting to see the emphasis that his group puts on things compared with ours, and they also do much more work, I think, on orbitraps than we do, although we've started this a little bit too. So Mike's going to give you a slightly different perspective on the way they do DIA. Mike, please.
Great. All right, thanks. It's great to be here, and also great to see so many people who are interested in this new data acquisition strategy. I say new, but it's actually been around for kind of a while. It's just to kind of gained a little bit of resurgence as instrument hardware is kind of caught up with kind of the ideas and the methodology. And then also, of course, a lot of software is finally getting caught up to some of the ideas as well. So I'm going to give you a little bit of an overview from our perspective on DIA. I'll give you a little bit of an introduction on orbitraps, and also a little bit of introduction of what we mean by peptide-centric versus spectrum-centric analysis. This will kind of feed into a couple other discussions that occur later on in the week. Okay, so these are basically the way I think about the three main data acquisition strategies you'd use on an orbitrap mass spectrometer. There's, of course, the most common data-dependent acquisition, where you semi-randomly trigger MSMS dependent on events in the MS1 space. So if you ran the same sample twice, you probably will not get the same pattern of MSMS sampling. You also won't get MSMS sampling continuously over time, so your ability to do quantitation on the MSMS level probably would be very poor. So we think about this predominantly as the data going into a database searching, doing peptide identification, and most of the quantitation, with the exception of TMT, is done on the MS1 level. We can talk a little bit more about that later. The other extreme is targeted mass spectrometry, where you have a hypothesis for certain proteins or peptides that you're interested in, and you tell the mass spectrometer to measure certain mass to charge continuously over time. You sample those continuously over time. You then perform a targeted analysis where you extract the chromatograms for targeted B and Y ions. You then use that to then define whether or not you can detect a given peptide, and also use the area under that curve of the MS data to provide a measure of the quantitation. A more recent alternative to this, if you want to have a more comprehensive sampling of the data, is, of course, you sample using data-independent acquisition. Here, what you're doing is you're intentionally increasing the width of the windows to multiplex the MSMS, so you're intentionally making it so you sample more things at a given point in time. Each mass spectrum is now intentionally a chimeric of multiple different components. And then you still analyze the data. At least in our perspective, we analyze the data in a targeted analysis where we have a target peptide of interest. We extract those individual chromatograms. We make decisions based on which peptides or which product ions don't have interferences on the actual data itself. We use the area under the product ions to determine the intensity. So that's, I think, a little bit the way we have approached it. We've always approached it this way. We've approached it as a way of being a comprehensive way of sampling the data with MSMS, where we then, it's more analogous to that of doing parallel reaction monitoring, so we can go back and target or extract chromatograms after the fact. So again, one of the problems we have, of course, is that we've given data independent acquisition so many different names. So this kind of gets confusing. It's data independent acquisition is the term that John Venable gave in 2004 for the sampling idea on linear ion trap mass spectrometers. The Bruce Lab, I think it was around about 2010 or so, had what they called all reaction monitoring, Jim Bruce. They were doing it in FTICR instruments. And of course, there's SWATH, HRM, there's other terms. But they all basically mean the same thing. Also, there's MS-E, of course, by Waters. So the idea here, the simplest way that we tend to think about DIA, a very common but simple acquisition that we've used in our lab, is to measure sort of all the mass range from 500 to 900, using 20 mass charge wide windows. So this is 400 mass to charge. You can span this on an instrument that measures things at about 10 hertz, about every 2 seconds. So you can measure all the fragment ions for all the precursors between 500 and 900. And this type of acquisition has been performed on basically every type of mass analyzer that can measure an intact full spectrum at a time. So originally this was done on linear ion traps, then it was done on FTICRs, and more recently it's being done on orbitraps and time-of-flight mass spectrometers. We started doing this back on linear ion traps, but we've now, of course, predominantly our lab's been doing this on orbitrap mass spectrometers. So we have a lot of experience with this. If people have questions, I'm happy to try to answer in more detail. So if you're trying to span this mass range, we collect them in the simplest way. We'll talk later in the week about some more fancy or advanced data acquisition strategies. But the idea is that you collect them all in series, and then when you get back to scan 21, you start over again. On a Q-exactive type mass spectrometer, this in general gives us about an acquisition every 2 seconds. It's not ideal, but it's not the worst thing in the world. And with an orbitrap, you're basically having the quad filter isolate a fairly large window of 20 mass to charge. Most of the masses get blocked, but there is a set of fragments of precursors that will pass through the first quad. You subject it to beam CID, or thermal calls this HCD. You then get a set of chimeric set of fragments that you measure in a single mass spectrum. We also throw in the MS1 scans just for good measure. And so there's a couple characteristics of this that are kind of important. One is we can get comprehensive MS1 and MS2 sampling. I would never call it comprehensive proteomics because there's a lot of biases that occur in any of the sample preparation and the sample measurement, but we are comprehensively sampling everything in that mass range within the cycle time. So in this case, it's around about every 2 seconds. The MS-MS events are untargeted. So what do I mean by untargeted? So in a DDA experiment, we trigger an MS-MS event centered on the target of interest, defined by the MS1. In parallel reaction monitoring, we target it, so we center that isolation over the precursor of which we have a hypothesis that we're interested in. So our isolation now, our targets could actually be off to the left of the actual center of the window or to the right of the window. It doesn't really matter as long as it's actually in the window somewhere. Now, this does have some extra complications as far as the isolation window, but we can talk about that later if people have questions. It's also unbiased. So we're going to trigger an MS-MS event regardless of the intensity. So if it's a small signal, a medium signal, or a large signal, or even if there's no signal that's detectable in that isolation window, we're going to trigger an MS-MS event. It's got wide isolation, and this is one of the defining characteristics, actually. In general, the selectivity is a lot worse with data-independent acquisition than with truly targeted analyses. So it's about 20 mass to charge isolation. The other characteristic events of it is that it's consistent sampling or systematic. So we're basically selecting MS-MS events over time. So I've got this arrow of time over here. In an approximately 2 to 2.5 second time scale. And because of this, we can then use the data to reconstruct chromatograms from the product dyne data, which got for us pretty much superior sensitivity and quantitative precision. So if we think about this, the way that we actually use this data isn't to tell us what types of things can we identify, it's to tell us what sort of things we can detect. So we'll often start with some sort of hypothesis, which we're saying, can we detect this target peptide? And it could be this target peptide and 1,000 others. But in general, we approach this question in a very targeted way, is saying, can we measure this specific peptide? This peptide has a doubly charged precursor of 790.4. It would fall in this isolation window. We could predict then the B and Y ion fragments. We can then go across all of the precursor MS-MS isolation windows, and we can then start to extract the B and Y ions across time. Of course, this is in 3 dimensions. So the data is actually 4 dimensions. We have precursor mass, product dyne mass, retention time, and intensity. I'm displaying here 3 dimensions for any one individual precursor. What we display this, obviously, in a tool like Skyline is in 2 dimensions. So we're basically looking through the data in this dimension right here. We collapse it, and we color code these individual chromatograms across time, but they reflect and are measured by different product dyne masses. So another way to think about this is that you're actually collecting parallel reaction monitoring or selective reaction monitoring data on everything. So here we actually measure individual precursors where you can go in and pull out that individual chromatograms and determine whether you can detect or quantify the peptides. Another aspect is that we can actually go through any of this data within any of the mass range and pull out chromatograms from any precursor or product dynes that we have any hypothesis of whatsoever and determine whether or not we can detect and quantify it. So if you think about this in a targeted experiment, so the difference between a truly targeted experiment done on a triple quad or parallel reaction monitoring is that this is a truly targeted experiment. This data acquisition and isolation is untargeted. We're not centering the isolation window. This has got a wide isolation window versus this has got a narrow isolation window. The mass analysis of a selective reaction monitoring experiment is done with a mass filter. And it's also done at unit resolution. But basically the quad only measures 1 mass at a time. But then we go and we obviously reconstruct product dyne chromatograms. With a orbitrap, we collect the entire spectrum at each time. We then do target extraction on the data. The obvious advantage, of course, in doing this on an orbitrap or a time-of-flight instrument is that we collect the entire spectrum all the time. So you can obviously adjust which product dynes you extract depending on the actual results of your data. But ultimately, the data looks very similar. So we've actually always thought about this as being truly a targeted experiment. Okay, so what are some of the advantages of doing data-independent acquisition? So I've always liked this slide that Jared Egertson made, and Jared was worked in our lab for about a decade. And one of the things that he used to always bring about is that when we were doing targeted experiments, we start that experiment with a hypothesis. Someone tells us we want to build an assay to measure a certain protein. We have a hypothesis that a certain set of proteins should be changing. We want to measure proteins in a certain pathway. We start with a peptide, and then we go through all this huge process of assay generation. So we have to figure for those individual proteins, what peptides will we end up using? Will we go through retention time scheduling? Will we have to refine our transition selection, et cetera, before we even get to the point of analyzing our set of maybe 100 or 1,000 samples that come into the lab to deal with this data? We then go through peak integration, data analysis on our set of proteins that have our hypothesis. And then sometimes, of course, you either find things that are changing or are not changing. Then you use that to refine your hypothesis. You say, oh, do you want, we should go back and build a new assay to measure this modified form of the specific protein, et cetera. So data-independent acquisition was extremely appealing to us because what happened is our lab started to just acquire the data. We acquired the data on our samples, sometimes 100 to 1,000 samples. We would then use that to generate a hypothesis. We'd go through the peptide selection, chromatogram extraction, peak integration, sometimes transition refinement. And then we would generate new hypotheses, but instead of going back to reacquire the data, we would just go back to redo the analysis. We have lots of examples where we've collected data for things, and our collaborators have come back and said, look, is the oxidation on methionine 80 changing during these different conditions, et cetera? There's a brand new paper that shows an alternative splice form that's shown, can we detect an alternative splice form that's present in these samples or not? So these are sort of things that we began to do quite regularly. And as while we don't offer a core service, we found that if we did offer a core service, I would have thought this would be particularly appealing because you could collect the samples once, you could train your users to analyze the data, sort of like how you're learning here, what Brendan's doing with a tool like Skyline, and they could then, in theory, go back and remine their data over and over again. Does that make sense? So this was something that was particularly appealing to us, this idea that we could basically do a target experiment, but this assay generation is challenging, it's difficult. This meant that our data collection aspect became fairly easy. The biggest challenging part then became after that was actually interpreting of the results and then basically going back and redoing the analysis. But the data itself was fairly easy to collect. Okay, so the promise of data independent acquisition. So I love that when Ludovic's paper came out, they used, I think, this term, or was at least used up around that period of time, this idea of a molecular image or a digital archive of the sample. You can mine it over and over. There's no issues with scheduling. The scheduling is kind of the complexity of doing truly targeted proteomics, because in order to get good scheduling, good quantitation, you need to measure your analyses over just a narrow period of time. And the reason why I have this picture of the Mona Lisa here, because I began to think about at the same time the efforts that a lot of the large cloud companies were trying to make to kind of digitize almost everything. So Google made this big effort to try to digitize books. They would scan enormous volumes of books so that all the books were available. They would go through all the libraries, every new book that they could find, every old book they could find, every permanent record, they would scan it, and then use that so that people could go back and they could find it. If something ever happened to that book, there was a permanent record of it. They also, at the same time, began to digitize permanent work, important works of art. Of course, like the Mona Lisa or Picasso's famous paintings, and the idea there, of course, is that they wanted to permanently record these things in case there was ever some damage or there's issues with it. They would always at least have a permanent record of it. So you can also then do direct queries for peptides of interest. So you could go back and reinterpret what may be there. You can look at the photograph or the painting at different time from different places, etc. And of course, the other promise of DIA is that the quantitation is better than doing data-dependent acquisition, and I'll talk about that in a bit. So I do want to give one example of how you might want to kind of interrogate data after the fact. So not just in the case of digitizing works of art or books. Google and other people who are trying to make these they're called gigapixels. They also are trying to generate permanent records of events in time. So this is a gigapixel image that was generated of the U.S. inauguration in 2016. We're still kind of suffering from that a little bit. But if you go into these images, regardless of your politics, are pretty incredible, right? You can blow up this image and you've got this incredible record of everything that's in there. You can go look for different people in the image. The resolution's absolutely incredible. You get this record, that permanent record that's there, and you can go back and look for different people in the audience, what their facial expressions were, etc. Now, of course, some people must say, well, you could have taken an image with a telephoto and looked for certain specific people in that image. And that's true, and I would call that is the equivalent of doing things by parallel reaction monitoring. You can collect an image with a telephoto with incredible resolution and quality from a far distance away, but you don't have then the luxury of being able to go back and look at the greater image and to consider other possible things that may be in that image or photograph. So this is basically what the kind of the holy grail is for data independent acquisition. It's this ability to collect a really high resolution molecular image that you can interrogate for specific analytes at the beginning maybe, but then over time potentially go back and reanalyze for different analytes. So things that you can do now post-acquisition, you can choose different peptides for a protein. Let's say certain peptides don't show very good correlation with disease. Maybe there's different proteoforms than what was expected. You could choose different transitions. Let's say a couple transitions had interferences with them, so you can go back and pick different transitions. You can't do that by selective reaction monitoring. You could add different proteins or proteoforms as they become known. We don't know much about proteoforms, but people are collecting more and more data about them, and the quality of the data is getting better and better. People are finding new alternative splice forms, and we'll be able to go back and interrogate those things as new data becomes available. Okay, so this is something that isn't always intuitive for everybody. The plot's going to take a little bit for me to explain. So what we did is a fairly simple experiment. We took about 660 peptides that Brian Searle was pretty interested in within the lab, and he performed parallel reaction monitoring on them. He did 0.7 mass to charge precursor isolation on 660 different peptides through many different injections to measure the quantity of them between a series of different samples. And we assumed that that was basically the best case scenario. We're using a high resolution, accurate mass analyzer. We're using a narrow quad isolation on the precursor. We're measuring the different conditions that we're measuring with parallel reaction monitoring. We also did that same exact analysis by data-dependent acquisition in a single run, and we also did it by a number of different methods for doing data-independent acquisition. The key thing here is not about these different methods. We'll talk about some of those in a couple days from now. But the key thing is that all of the data-independent acquisition methods gave basically the same trend. So here is the percent of quantifications, and here is the deviation from the measured ratio versus the true ratio, and the true ratio here is assumed as the parallel reaction monitoring. So, when you're using, and the DDA, I'll say, is that the quantitation is done with the MS1 data, and the MS1 data is limited significantly, at least on ion trapping mass spectrometers, by dynamic range and also selectivity. Right? There's lots of things that have the same mass, but not that many things that have the same precursor mass and product ion mass. Okay. So the percentage of the quantifications that actually gave the ratios similar to that of the parallel reaction monitoring were fairly high by data-independent acquisition, regardless of the data-independent acquisition methods that were being used. So ideally, if everything was just as good a quantitation as parallel reaction monitoring, we would see a horizontal line here, and it would go straight up. So there is some deviation. There's a certain portion of the quantifications that deviate a little bit from that of the parallel reaction monitoring data. But in general, it's doing much better than that of the MS1 data, which deviates a fair amount of the measured peptides deviate significantly from that of the parallel reaction monitoring data. So MS2 quantification is more sensitive, and it's also more accurate. There's at the low end, the difference is from the actual measured ratio becomes smaller, more things get what people often call ratio compression, but in general it's because one of your two components is below the limit of quantitation and the other one is above. Yeah.
So just to orient myself, I've seen this plot a few times, but as soon as it crosses the one line, that's a twofold change, right?
That is correct, yeah.
And those are peptides or those are proteins?
These are peptides. They're all phosphopeptides. There are 660 phosphopeptides. Yeah. Yeah, so that just shows you, I'm not saying that data-independent acquisition is perfect, and I'm also not saying parallel reaction monitoring is perfect and is the actual right answer either. It's just saying that we are expecting that is going to be the best case scenario in this case. And so if you are looking at twofold deviation from the parallel reaction monitoring data, it still does have some sort of deviation. That's using the MS1 quant. Yeah. Yeah. Yeah, and we have actually lots of data like this now. The MS1 quant, especially on orbitrap data, have significant limitations as far as the dynamic range, mostly because of what people call the space charge limits in the orbitraps. You can only put 1 million charges or 500,000 charges in the instrument. So if you've got a lot of things when you measure data-independent acquisition, we're filling that same number of ions over a narrower mass range. Okay, so the key thing here is now how do we think about analyzing these data? And so I think this is where some of the things have changed substantially, I think, in the last, I would say, decade, substantially over the way things had in the past. One key component is I would say that we don't think about analyzing these data as how many things do we ID? We're thinking about things as being, can I detect the peptide? And if I can detect it, can I quantify the peptide? So those are two things. If you just assume, for example, everything's there, can you detect it? Can you quantify it? So let's say you walked into a library. This is an analogy that Jared Egerton always used to like to give to. And you wanted to go find a specific book. The equivalent of data-dependent acquisition would be is if you told the librarian to go into the library and pull out a bunch of books randomly from the shelves, and then you'd go and look at the titles on those books, and you'd see whether or not your book's there. So this isn't ideal, right? Because your chances of randomly selecting your book isn't that great unless, of course, your book's present in the library at a fairly high frequency, which, of course, it probably isn't the book that you're interested in. So the conclusion may be incorrectly drawn that, that Harry Potter, this book, was not identified, so the library doesn't have it. Right, of course, this makes no sense whatsoever. You would never think about this way, which is why just because you don't identify a peptide by data-dependent acquisition doesn't mean anything about whether or not it's present or absent. It only means something if you can identify it. Then you can say it's present. So because of that, that became, of course, very interesting in order to come up with different alternative ways to analyze this data. So we began to think, okay, well, what if we knew a lot about the peptides already? What if we knew things like the retention time? What if we knew that it was already determined that other people have found that protein or peptide in that given sample plenty of times previously? What if you knew things about the different product ions, which product ions were intense or which ones were not? These are all what people call in the computational field as priors. So you basically have all these priors about things that you have known about it. So just like this, let's say you knew how the library was organized. And if you knew it was organized alphabetically, you could then say, look, I can go very specifically to the library at a specific place, and I can then say whether or not in that small area which it was expected, whether or not the library has it or not. Okay? If you have less priors, like if you don't know how the library is organized, then you end up having to spend a certain portion of your time looking randomly around the library to see whether or not you have it or not. So the idea here is, can we make use of prior information that we know about expecting where a peptide should be, where it responds, which peptides respond well for given proteins, in order for us to be able to expedite and improve our ability to, one, detect it, and then to quantify it later in future experiments. Okay, so let's just show this a slightly different way. So we wrote this paper a couple years ago with the Aebersold lab and Dick Smith's lab. We defined a couple of terms. We said that the way most people do discovery proteomics these days, we call it spectrum-centric analysis. You collect a bunch of spectra, and you take a tool like Sequest, Mascot, MaxQuant, and then you put those spectra match them and score them against a protein sequence database. And then for each one of these spectrum, you get one or more peptide spectrum matches. So for every spectrum, we have a peptide spectrum matches. And then for that, we can calculate an error rate, like a p-value or q-value. So it gives us a sense of whether or not what fraction of what we're calling correct is false. So what we're basically doing is saying, look, for this given set of spectra, what peptides best explain the data? An alternative to this was to actually go forward and take what we called a peptide-centric analysis. And that is, instead of starting with the spectra, we're going to start with the peptides. And now for every single peptide, we're going to score them against all of the data. And then for all of the data, we calculate a score. And then we use an ideal portion or region in time that we then use to then provide our evidence for detecting that individual peptide. So for this case, we have which peptides are detected in our peptide. And a key component here is that the null hypothesis is slightly different, right? So in this case, if we have a peptide that's below a given Q value, it means we have no evidence for this peptide. When in the more traditional sense, it means that the peptide spectrum match is incorrect. Does that make sense? This is it may sound subtle, but in this case, the peptide spectrum match is incorrect, is the meaning and the interpretation of the Q value, when in this case, the Q value means the peptide is not detected. So whenever you have a p-value or a q-value, you assign to a null hypothesis. That null hypothesis is in this case is the peptide spectrum match is incorrect. In this case, is the peptide is not detected. Now this is actually a much more meaningful null hypothesis To actually have a statistical number that we can then put on the results that's saying we have no evidence for a given peptide is a much more meaningful result than that saying the peptide spectrum match is incorrected. Because in this case, we can't see anything about the peptides that were not returned from a peptide spectrum match. So if you have 10,000 spectra, you've basically only got even Q values for those 10,000 individual peptides. But if you've got 10,000 peptides you're interested in, you can either say yes or no to about those 10,000 peptides and whether or not you have evidence for them or not. So p-values are returned for every queried peptide. So you have a statistical metric about whether or not you believe each peptide is there or not, regardless of whether or not you've actually you've triggered an event on a given peptide by DDA. So another problem with data independent acquisition is that peak picking is challenging. So let's say you were looking for this individual precursor peptide and you extracted the MS1 chromatograms. This just gives you a sense of how complicated these mixtures are. There's MS1 peaks, there's peaks at basically the blue is the M+0 mass, the pink or purple is the M+1, and then the other color is M+2. These are the different predicted B and Y ions. So if you had no other pieces of information associated with it, it would be very hard to basically be able to say that this signal right here, right around 40 minutes, actually belongs to the target peptide of interest. The MS1 is completely unresolved from other interferences, and the MS2, while it's there, and they all are co-eluting, and there are product ions that don't have interferences, would be very difficult to pull out of all the other components that are present. So there have been lots of software tools now that have been used to kind of deal with this. There's been, so those that are, we call peptide-centric, those that say, do I have the specific peptide? There's tools that are, Jim Bruce's lab had this tool they called FT-ARM. Our lab had a tool that we published called Pecan. There's also those that make use of prior information, which I said, look, we have a retention time. We have different known spectral libraries. Those are obviously OpenSwath, PeakView, Skyline, Encyclopedia, and Spectronaut. And then there's also spectrum-centric. So those tools that go and say, look, let me try to find those product ions and deconvolute them from the different mixture. And then I'm going to take it and apply a regular spectrum-centric search engine. So I've now got a demultiplex, deconvoluted product ion spectrum, and I'm going to take a tool like Mascot or Sequest or Xtandem and search it against that data. And the original case of this was MS3E from Waters, but there's now, of course, multiple different tools. Most commonly used one is DIA Empire, and also Biognosys has Pulsar, which is another tool like that. And so these tools, of course, are gaining definitely very interest because they allow you to take a traditional spectrum-centric searching approach. But the most common way people still try to do this is to take a spectrum library, a wide window DIA file. You extract chromatograms, you compute different scores, and you put this through some sort of machine learning classifier. OpenSwath and mProphet use a linear discriminant analysis or a support vector machine. And I just want to point out that you'll be learning more about this throughout the week, but Skyline really does implement the state of the art. It implements the same basic mProphet scoring that was published in the original SRM paper, and then of course it's been implemented and used by OpenSwath. It's a fantastic algorithm, so there's no point in we might as well make use of that great work that was done by the Aebersold lab. You can calculate, you can make use of different score features, you can retrain them, you can weigh them, you can see how the score distribution from the decoy empirical null fits the actual real data. You can also then look to see the p-values and story tips surrounding q-values. The other kind of key thing is that basically all of these tools, which are largely all based off the same original mProphet algorithm, all give basically the same results. So whether or not you're using Spectronaut, OpenSwath, Skyline, or Swath 2.0, which is the PeakView or SciAxis tool, They all give very similar results, either on the peptide level or on the protein level. Some tend to be a little bit more sensitive than others, but in general, if you look at them, they're all the numbers are fairly small on those that are unique to any one tool versus another. So one thing that's kind of really key to kind of keep in mind, and that is that data independent acquisition is all about balance and also about sacrifice. So one thing that we started originally with is trying to figure out what mass range should we actually end up covering. And we actually did an initial analysis that was based off of this paper here that Jesse Canterbury had presented and published in 2014. The data was collected around about 2010. This was done actually on linear ion trap data, and he basically did many different injections. This was basically similar to the Pacific paper from Dave Goodlet's lab, and spanned the mass range and throughout from 400 to 1400, and showed that this 500 to 900 range tends to be pretty rich in the peptides that we're end up measuring. This was with a different instrument, but we ended up using this plot a lot to justify this 500 to 900 mass range. And I'll show you another plot in a little bit that actually shows that we might want to actually go from 400 to 1000. But in general, this ends up being a fairly good range as a starting point for a lot of data independent acquisition. And the reason why this is important is because if you had to cover this 400 mass to charge range and you wanted to do it with 20 mass to charge wide windows, you also have to balance how many points across the peak you're going to get. And you have an instrument that scans at 10 hertz, so this is 10 MSM spectra a second. You would then get a point every 2 seconds. So in this case, if you had a 30-second wide peak, you'd have a point about every 15 seconds. Now, of course, you could scan 40 by 10 mass to charge wide windows. So now you get twice as many, you get half the window width, but it takes twice as many MSM spectra to accomplish that same mass range. And so now you get half the number of points across the peak. You're talking about 7.5, maybe even a little bit less. And if you even went to the point with 5 mass to charge wide windows, you would then, of course, get barely any points across the peak. And this, of course, may actually have a major sacrifice as far as quantitation goes. Another alternative to this, and we'll talk a lot about this a little bit more on Thursday, and that is you could potentially make multiple different injections to span this different mass range. This does come at the expense of throughput, but it definitely means that you get narrow isolation across the entire mass range. It comes at the expense of having to make multiple injections per sample. So why is this important? Well, this comes back to people may know about the Nyquist limit, and that is how many points you basically need to define a signal. So Matthews and Hayes in 1976 sort of defined that for a chromatographic peak, it basically meant that it was about 8 points across the peak. And so if you're using trapezoidal integration, like tools like Skyline do, you're basically, if you have on the order of around about 6 to 8 points across the peak, you're going to end up getting a fairly decent estimate of the peak area. However, if you undersample the peak, your area is going to become a significant under deviation, so underrepresentation of the actual peak, dependent on the number of points that you have. So this is a plot that Brian Searle had made using using theoretical randomly generated data, where he intentionally shifted the location of where he was sampling the peak, randomly sampling the peaks at different intervals, and showed that that you underestimate the area substantially unless you have about 8 points across the peak. 6 points is probably okay too, but in general, you definitely ideally would like 8 or higher more points across the peak in order to give you a minimal deviation from the true quantitative area. You can get some point in time you'll see within your quantitative data where you'll see some points that basically look like triangles, and that means you're significantly underrepresenting the peak area. Yep.
When you have less number of peaks, transformation, what you have in Skyline, does it help to make it better or?
It may look better, but Skyline, even if you're smoothing the data, you can't do anything about making up area. So the points are still being drawn at a fairly infrequent value. So yes, you can smooth the data, make it look a little bit more rounded, but in general, you're still going to underestimate the peak area. And in Skyline, it still does all the quantitative data from the unsmoothed data. We just use the smoothing to help pick the peaks and et cetera.
Meaning the computation that goes in is without smoothing.
That's correct. That should be done anyway, ideally. Yeah, so the isolation window width is very different. So narrow window by DDA. So often now with modern mass spectrometers, we're actually even dealing with even sometimes 1 to 1.5 versus data independent acquisition, which is anywhere from 5 to 10 to 20 master charge. So this is a big challenge, right? So each spectrum is hard to interpret by itself. So here's an individual 2 master charge wide window around this target peptide. Here's a 10 master charge. And here's a 20 master charge. So you'll notice that the individual product ions are there for the specific peptides. However, there's a lot of other things that are in there as you increase the window width. And so the wider that you open up the window width, the more challenging it is to be able to get product ions that are not interfered from the actual, from other interferences in the isolation window. Here's just another example of this right here. So here's a 10 master charge wide isolation window, and here's a 20 master charge wide isolation window. And so you're extracting the same product ion chromatograms, but here now, of course, there's another set of product ion transitions. While they are, you can integrate the signal separate from this one, it does make even peak picking even more challenging. And there's lots of times with the low master charge in particular that you don't even have interference-free transitions. So in this case, this interference right here falls within the isolation window. In this case, it falls outside the isolation window. Okay. So this is another case where we basically showed where the number of peptides that we can detect over 500 to 700 mass charge range. So this is a narrow master charge range using different MS-MS isolation widths. So in some cases, we made multiple injections to span the isolation window from this fairly narrow mass range. In other cases, so this took about a 4-second cycle time out here. In this case, we're doing a single injection to cover the mass range. But the key thing that's kind of the take-home message is that the narrower the isolation width, the greater the sensitivity. In fact, there's almost a negative inverse correlation with as the isolation width gets larger, that you begin to lose your sensitivity or ability to detect certain peptides. This makes a lot of sense. You're filling the orbitrap over a narrow isolation window. So the wider the window gets, the more likely there'll be other things that interfere with it, and the harder it's going to be able to distinguish your target peptide from that background incorrect signal. So another way to look at this is that if you had some sort of discriminant score for those peptides that are not present versus those that are present, you would have to draw a given line for a given false discovery rate that you might be interested in. As you narrow your isolation window, though, the peptides are going to become better separated. Your true peptides are going to become better separated from those that are incorrect. So you should be able to shift your false discovery calculation a little bit over to the left even more. We're not the only people who have seen this. So the quad isolation tends to take on is the biggest priority, I think, as far as the most important discriminating factor. So when you look about an orbitrap resolving power and that of the quad isolation window, this paper by Sebastian and Bruno Damon basically showed that when they were doing parallel reaction monitoring, that the quad isolation window is actually more important than that of the orbitrap resolving power. So if you look here, as you go from 24 mass to charge, so basically DIA type windows, your percentage of fragment ions that are going to be interference free is going to drop significantly as you go from 24 mass charge to 16 to 8 to 4 to 2. It doesn't drop quite at that same rate as you go from 70,000 resolving power, 35,000 to 17,000. So you're better off going faster with narrower isolation windows than you are at going slower and doing wider precursor isolation windows. In general, precursor isolation is more important than product ion resolving power. So what this basically means is that if we were trying to come up with a permanent molecular record of the Mona Lisa, what we're effectively doing right now is collecting a permanent record like this. So the data is not collected at very high resolution. It's really hard to even make out that there's a painting of a person there. We could collect the data at higher resolution, but we probably couldn't span the total image. So we're probably then only collecting a higher resolving power, but having only a portion of the total image. We could then make many different injections to span the entire image, but then that would become, of course, the expense of throughput. It would take a lot of extra time. So we do end up having to balance things quite a bit. We're either trying to make a decision is, should we do everything in a single injection to span the entire image at fairly low resolution? Should we be covering a portion of the image, so a narrower mass range, but at slightly higher resolution? Or do we make multiple injections to collect a full high-resolution image across the entire image? Does that make sense? Okay. Now, if there's one take-home message here for people who are doing using orbitraps, is anyone who here is using orbitraps? Okay, so it's a good portion of the audience. This is a really key figure. These notes will be made available, and it's something for people to kind of definitely keep note of. And that is, whenever you talk to Thermo, they'll tell you a fair amount about the scan speed of their instrument. But of course, that scan speed, the acquisition rate, comes at the expense of injection time. And this image is fairly similar on the QEHF, as it also is on the Fusion and also on the Lumos. But there's a kind of a couple key components here. One is that if you were to collect the data at about, say, approximately 10 hertz, you then now have the capability to do a maximum inject time, so an ion injection time of about 60 milliseconds. So if you wanted to span a 400 mass to charge wide window, let's say doing 20 by 20 mass to charge, you'd now get this key component here is 60 milliseconds. That gives you a lot of time to fill the orbitrap to hit your AGC target. If you wanted to go more like at 20 hertz, you'd be limited more to around about 17 milliseconds. So Thermo will make a comment and say that their instrument's capable of running at 20 hertz, a QEHF. And that's true, whether it's a QHF or QHFX. But the key thing there is that when you're running at that speed, it means now that your limiting factor is the maximum inject time. So you have to decrease the maximum inject time in order to gain actually the true benefits of that that scan speed. Okay. So now this becomes a really critical component because you have to make a decision. Is it better to have a longer maximum inject time and go faster, or is it better to go a longer maximum inject time and go slower, or to go faster and to have a much slower maximum inject time? So we've done, of course, different experiments like this. We've done 10 mass to charge and 10 mass to charge. We'll talk about this more on Thursday. The key component is when you do 10 mass to charge versus 20 mass to charge, this is 17 milliseconds versus 60 milliseconds. But when you do the slower acquisition in the wider window, we basically hit our targets almost all the time. So we hit the maximum AGC target, the 1 million ions charges. But when we run at the faster rate, at the 17 milliseconds, we almost never actually fill the orbitrap. And a key component of this is very different than doing DDA, because most of our time is sampled where we would not necessarily have triggered an MS event, because their MS1 signal may be very small in that isolation window, even though there's actually a decent number of ions.
Could you say something about what that sample is and the load and stuff?
Yeah, so this is a helocell lysate that was run with about 1 microgram loaded. Yeah. So I will point out that as you get to like the Lumos and the QEHFX, that sometimes 17 milliseconds is actually enough. But when you go from things on the QE-HF versus the QE plus, it definitely is not. The source not bright enough. No, so we'll talk about this a lot on Thursday. This is kind of a little bit too early, but we actually overlap them by 50%, and we sort of half and half, and we'll talk about the reason why we do that on Thursday. I had this figure from a previous thing, but I'm not going to get to that until Thursday. Yeah, no, we actually overlap them by 50%, and we do a deconvolution step in there. Okay, So one of the things that we wanted to do when we first got our Lumos in the lab was to kind of evaluate a couple different things. So one was the precursor selectivity versus cycle time. The second was the fragmentation method. And the reason for doing the fragmentation, I think I've already kind of pointed out why the precursor selectivity versus cycle time. The fragmentation method is important because the Lumos can actually collect data by a couple different ways. It can actually fragment things by beam CID. Thermo calls this HCD. It can also do resonance CID, which basically activates just a single frequency and gets a different way in which you collect fragmentation spectrum. So we wanted to be able to compare those two different fragmentation methods. We also wanted to be able to compare product ion selectivity. Now, the reason why we wanted to be able to look at the fragmentation method, and that is because when you look at HCD, you're normally, when you do data-dependent acquisition, the instrument automatically triggers a given collision energy dependent on the determined charge state from the MS1 signal. So you may actually have the optimal collision energy for a given peptide of a +3 or +4 or +5 precursor that's stored in your library. But when you do data independent acquisition, because you may have 10, 15, 20 different things within your isolation window, we just apply a single collision energy. In our case, we apply it optimally for doubly charged. So what we've shown here is a plot showing the deviation from the optimal spectrum, so Pearson's correlation coefficient, from that of from the spectrum that's in the library versus that's just collected by the chromatographic data. So you notice that the doubly charged precursors by DIA correlate the best relative to the spectra that are within the library. That's because the doubly charged will be the same collision energy of that in the library. The triply charged features that are collected by DIA correlate less well to that within the library. The quadruply charged correlate even less. So this was a reason why we were thinking about potentially using different collision energy, different activation methods, because resonance CID is completely independent of charge state. So on a fusion Lumos, resonance CID is slower, beam CID is faster. Collisions per precursor ion, you only ever get one fragmentation, one bond break. As soon as a bond breaks, it's off resonance. You get, with beam CID, if you have too high a collision energy, you get only low mass fragment ions. If you have too low, you only have precursors. There's no charge state dependency based on resonance CID. There's a high charge state dependency on beam type CID. Also, beam type CID, you get low mass like ammonium ions, etc., but you get very little B ions. Resonance CID, you definitely get good use of B ions. So this was the basic method. We had different isolation widths. We did things with single injection, with 2 injections. We also had different methods. So the 2 mass to charge. You notice that in all cases, the resonance CID gave a slower cycle time than that of the beam CID. We also looked at the number of peptides that were detectable, and in almost all cases, the resonance CID gave slightly better detections than that from the beam CID, but it was never really termed in our case enough to be significant. So we actually always end up sticking with just doing the beam CID, mostly because it was faster, and for us, quantitation was more important than the number of peptides that we could detect. And so if you think about having a cycle time of about 3 seconds would be your cutoff for what you'd actually want to consider for doing quantitation, that basically left us with multiple injections at either this 3 or 4 mass to charge isolation window width, or 8 or 10 mass to charge for a single injection. The big difference here, of course, is that as the isolation window gets much larger, the number of things that you can detect shrinks quite substantially. So for quantitation, this basically leaves us with these basically couple of methods. We are spanning just a fairly narrow isolation window, so just 500 to 700. Another kind of key component here is that if you used, this is data at a non-optimal charge state for beam CID, there's less overlap than that for which resonance CID. So the key component is that resonance CID doesn't really care about charge state, beam CID does, but in the end, the difference for us was less important than the actual overall speed. So the other thing here was the resolution. So at 30,000 resolving power, we could collect data at 10 hertz. We can do a maximum inject time for 55 milliseconds. For 15,000 resolving power, we could collect data at around about 20 hertz at about 20 milliseconds maximum ion time. It turns out that in all cases, the maximum inject time of 55 milliseconds and the higher resolving power were better off than doing things at a smaller maximum inject time and a lower resolving power. So getting more points across the peak, which is the only benefit of what you'd actually have here with the maximum inject time at 20 versus the resolving power of 15,000 resolving power, was the only benefit you gained, is that you gained a cycle time that was twice as fast. I think the quantitation will be even more dramatic, just because with a maximum inject time of 20, while you may have twice as many points, all these have enough points to define the peaks. They're all above the 8. So it does reach that kind of plateau. And so what this just means is that we're now dealing with less ions, but we're now at like 16 points across the peak as opposed to 8. So. Yeah. And so the key component here is that yeah, this is just that in general the things that we can detect span a broader range of intensity. So we can detect lower abundance molecular species with the larger maximum inject time than we can with a small maximum inject time. Okay. Yeah, and this basically just shows that that the percentage of the spectra that fill the orbitrap is much higher at the range where our peptides were predominantly eluting than relative to the maximum inject time. So we're underfilling the orbitrap substantially with the maximum inject time of 20 versus the maximum inject time of 55. Okay. Yeah. So the key conclusions here is precursor selectivity is more important than cycle time. Fragmentation method, residence CID, is a little bit better than beam CID, but we still end up sticking with beam CID because that allowed us to get back some of the cycle time that was lost from the precursor selectivity. And that product ion sensitivity and resolving power is actually, when you actually are filling the orbitrap, is more important than max inject time. But though in general, how we gain the sensitivity in the first place is using high maximum inject time. So we do have a set of recommended starting points. Again, this slide will be made available too, and as with all the other slides. And that is, though, we tend to go from about 400 to 1,000. We tend to start with about 24 master charge isolation widths. We'll talk a little bit about how we deal with some of these wider window widths in a bit on Thursday. We tend to do no margins in general. This is in contrast to other methods, and it largely tends to be whether or not we have a segmented quad or not. We tend to overlap the windows, which we'll talk a little bit more about on Thursday. Depending on whether or not you have the high field orbitrap, it tends to be at either 17,500 resolving power or 30,000 resolving power, and we tend to at times use maximum inject time that's as fairly large. So although sometimes on the QEHFX and on the Lumos we'll tend to go with the slightly faster acquisition rates because we can sometimes get by, but this relies on a fairly complicated mixture. We've also kind of gone back and evaluated the mass range aspect a little bit, and that is we analyzed data from 500 to 900, 400 to 900, 400 to 1,000, et cetera. But one thing to keep in mind is that as we go to a wider range, because we want the cycle time to be essentially the same, we actually have to open the isolation width. So 500 to 900, we're basically doing 25 by 16 mass charge wide windows. 400 to 900 is 25 by 20. 400 to 1,000 is 25 by 24, et cetera. And so what happens here is you tend to get this leveling off when you use what we call chromatogram libraries, which we'll also talk about on Thursday. And in general, there's very little benefit from going and covering a broader mass range over than the 500, 900 if you're using a traditional spectrum library. But in general, this 400 to 900 or 400 to 1,000 end up being a fairly good mix, what we've decided to settle on, at least in the lab for now. Okay, So I'm going to stop there for now. Since this is the end of the hour, I'm around all day. And if people have questions, I'll also be back on Thursday and talk more about different applications on orbitraps.
Great, thanks, Mike. A lot of good details on orbitrap. Are you going to publish that table? That would be nice for people to have,
so
right?
we actually have it on a website right now. We actually have if people are interested, we actually have it. In fact, we should put it in the notes of the course notes.
If you send me a link,
we have about a 20-page document on how to set up your orbitrap for doing DIA analyses. So we will make sure that the PDF gets made available for all attendees of the course. It definitely has been a huge help, and it saved us a lot of answering questions from. And this table right here is from that document.
Great. Other questions for Mike?
So at one point, I think slide 49, you showed negative correlations.
Negative correlation. Yeah. Yeah, I'm not sure about why there's negative correlations. I'm assuming that those are just incorrect matches. Yeah, I think what this is basically saying is that I think the key thing that I always take home is what's on this far right, and that is that the fraction of the things that are matching. There's a higher fraction of things. These are where you'd consider being correct, a correct match. Anything that has a correlation coefficient greater than 0.8 or 0.9. Anyway, so it's only the things down here that you're actually really looking at. But that it means that the fraction of things that are doubly charged in the chromatographic data that are matching with a high correlation coefficient in the spectrum library is much higher than that are +3 in the chromatographic data that are +3 in the spectrum library. And this is because the spectrum library data was collected with a DDA collision energy that was optimal for +3. And of course, with the chromatographic DIA data, it was collected at a collision energy that was optimal for doubly charged. Does that make sense? This is kind of a key component, and this will kind of lead into some things like how we're. So what I'm presenting a little bit are some of the problems that we have with doing DIA on orbitraps today. But at the same time, what we'll do is how we're trying to wrestle through them and improve upon them is going to be more on Thursday. Some of the more advanced topics. Yeah. So the question is did we try to vary the isolation widths across the mass range? In fact, there is actually. Oops, way back. So this is the variable DIA versus the normal DIA. Our lab uses a strategy, which I'll talk about on Thursday, where we actually overlap the isolation window. It turns out that we found that overlapping, at least in our hands, tends to outperform using variable width windows. But the reason for doing that is that if you have a 24 mass charge wide isolation window and you overlap it by 12 mass to charge, you can actually figure out which half of the window the fragment ions belong into. And so we have a manuscript that's just about to get submitted on that. We've been doing it for a long time, but it's taken us a long time to get the manuscript finalized. But the variable window widths, we can definitely handle the data from variable isolation window widths. But quantitatively, the nice thing about this is that it actually doesn't really make that difference anyway. So what we've found is it's easier to be able to detect a peptide using narrower isolation windows, but the effect on the quantitation hasn't been that bad either way. So, and the reason why this is because we have, let's say you have a 20 amino acid peptide. You basically have 40 fragment ions from the B and Y ion series that you can choose to use as being reflective of that peptide sequence. And if you wanted to use 5, if you have interference in any one of those 5, you can choose another set of product ions to use for quantitation. So what this basically assumes is that it's looking for product ions without interferences, and that even if you have a poor product ion resolution, you can pick other product ions that give you a good reflection of the quantity. That's actually a really kind of key component of why parallel reaction monitoring has become so popular over selected reaction monitoring. It's not because of anything else other than if you have interference in a product ion, you have the entire spectrum there, so you can go and pick different product ions for quantitation. And that's actually, I think, really powerful method. Did I answer your question? Okay. Yeah. So I guess I'm not entirely sure I understand the questions. Oh, yeah. Yeah. The problem is that there's another variable there, and that is the mass range covered, right? So you have 3 variables, right? There's the mass range that you want to cover. There's the cycle time, and then there's the isolation width. So I can't really tell you a single point. It's just that in most cases, when we collect the data at 30,000 resolution with a 60 milliseconds maximum inject time, the instrument will run at around about 10 hertz, right? So at 10 MSM a spectra a second. So if you have 20 spectra that are being collected, it'll take about 2 seconds per cycle time. If you collect the data at 20 hertz, you're limited to being about 15 to 17 milliseconds maximum inject time. So you're going to have a much less sensitive acquisition, but you're going to collect data twice as fast. So you could cover twice the mass range, or you could have half the window size. So there's 3 variables there that you need to play with. There's the cycle time, there's the mass range, and then there's the isolation width. So we're working on a lot on methods that allow us to narrow down the isolation width without increasing the cycle time or decreasing the mass range.
So do you suggest to have separate methods for identification and quantification based on?
Bingo, yeah. We'll talk a lot about that on Thursday. Yeah, so in our lab, what we've done a lot with is we've separated the detection from the quantitation. And we'll talk a lot about that on Thursday. That's a great point.